Assalamualaikum warahmatullahi wabarakatuh and a very good evening to all our audiences. Welcome to Bicara Pakar UIRL 2022 webinar. This is the first series which is brought to you live through WebEx, FB Live or Department of Deputy Vice Chancellor Research and Innovation UTM and also University Laboratory Management Centre PBMU. You can also catch up our upcoming webinars in our FB page so that you will not be missing out of any updates. Ladies and gentlemen, I'm Zaiton Bt Abdul Majid, Science Officer in URL and the moderator for today's session. On behalf of PPMU UTM, I would like to extend a very warm welcome and thank you to all of you for joining us today. We really appreciate your precious time. Before that, please mute your line to prevent background noise from disturbing this session. For your information, this webinar is conducted in a series. Starting from year 2021, this series is successfully organized with thousands of audiences who have joined us. We have called upon various kinds of field expertise among UTM researchers who have been appointed and collaborated with URL. Just to share our latest achievement, I'm proud to announce that URL has been awarded with ISO 17025-2017 Malaysia Laboratory Accreditation Scheme SAM in 2021. For the year of 2022, we have 4 slots altogether and the first slot was successfully organized yesterday by Dr. Zamri. If you missed it yesterday, we will upload the video in our URL YouTube channel. And to this Bicara Pakar UIRL webinar, we will bring to you another interesting topic to be shared with you. Before that, I would like to welcome to our honorable speaker, Associate Professor Chemist Dr. Zaiton Bt Abdul Majid, the Associate Professor of Faculty of Science, UTM Johor Bahru. How are you, Doctor?
Alhamdulillah, thank you, Ain. How are you?
Alhamdulillah. Thank you for joining us today. I believe that the topic that you will share with us can be one of the important sources and knowledge for us to improve our research field.
InsyaAllah.
So before I hand over this webinar to our speaker, let me share a short announcement. This webinar will be around 1 hour and 50 minutes and 30 minutes for the Q&A session. Those who have a question, please write it in the chat box or comment in the WebEx on FB Live and I will raise your question to our speaker right after the session. Attendance will be shared in the chat box 30 minutes after the webinar begins for UTM, CPD and Acap points, along with the purpose of e-certificate and sharing the video link as well. So please stay tuned until the end of webinar because we have lots of exciting quizzes that you can win and the question will be given to our speaker along the session. Right, Doctor?
InsyaAllah. Okay.
Okay. So let me introduce our speaker for today. Dr. Zaiton Abdul Majid is an Associate Professor of Chemistry at the Department of Chemistry, Faculty of Science, University Technology Malaysia. She obtained her Bachelor and Masters in Chemistry from Western Illinois University, United States and PhD in Civil Engineering from University Malaya. She is currently a Dean, Faculty of Science UTM and Associate Member of Academy of Science Malaysia since 2018, Member of Malaysian Institute of Chemists, Analysts and American Chemical Society. She was one of the 4 recipients and the first from Asia to be awarded the Lisa Meitner Guest Professorship Award, Lund University, Sweden in 2014. She was also a visiting scientist at Kyoto University in 1993, 2013 and 2015. She has appointed as a technical committee under Department of Standards Malaysia for the Standards and Metrology Institute for Islamic Countries, Turkey, 2017 until 2019. Her research focuses on 2 main areas of waste utilization. Example, development of solvents from waste, specifically focusing on separation sorption technology in water treatment and utilization of water as cement additives, particularly focusing on their effect on cement hydration reaction. Her research is multidisciplinary in nature with collaborators from science and engineering backgrounds. To date, she has a high index of 21, 64 international journals with impact factor ranging from 0.52 to 13.271, 3 book chapters, 2 books, 1 encyclopedia, 4 entries in Science and Technology Encyclopedia EST in Malay language, 16 conference proceedings, international and national proceedings, and technical reports. She is actively involved in STEM programs at the national level for the community, especially school and preschool under KEMAS. So, without further ado, I hand over this webinar to Associate Professor Cabis, Dr. Zaiton, with the topic Understanding the BET Surface Area. Now, Doctor, the floor is yours.
Okay, thank you, Miss Ain, for the kind introduction. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera and a very good afternoon to all. I'm Zaiton Bt Abdul Majid from the Department of Chemistry, Faculty of Science. Okay, welcome all. Okay, let me share my slide. Okay, let's start now. Okay, so the topic today is understanding the BET surface area. Now, the BET stands for the name of the 3 persons who are responsible for the development of the BET surface area technique. So basically, if you look at the name here, BET, there it stands for the last name of Stephen Brunner, Paul Hugh Emmett, and also Edward Teller. Now, the specific space area of a substance, or let me just abbreviate as SSA, is very important throughout all kinds of industries. Yeah? Now, even though the determination of the surface area is well established, okay, the method is well established. We see it often in journals, people, researchers, companies report as specific space area. But then it is worth taking a deeper look into the challenges that come with determining the specific space area, or the SSA, or the BET space area. So the outline of my talk today will be basically on the introduction, application of the BET space area, a bit on historical development. I like a bit on history, the absorption process. Actually, we have covered the absorption process the last time on Bicara Pakar, but just go through a bit. Assessment of the BET space area, theoretical basis of the BET method, and also on sample analysis. We'll show you a few examples from the literature. Okay. Right. Now, why is it important to determine the specific space area? Okay. Now, we know that surface area and porosity are physical properties which impacts the quality and character of a material. Okay. A solid phase material, any porous material. So materials can have identical weight and volume, but they may differ in surface activity and also absorption and volume due to their specific space area. Space area is a very important property of material. For example, during processing, or in companies during processing, or maybe you may be doing your work in research, you maybe want to synthesize your material, especially, for example, if it involves particle size reduction, the specific space area of your sample or product can also change. And any subsequent change during the manufacturing process or during your experiment will affect the porosity as well as the surface area. So these changes can lead to unexpected change in characteristic or desired performance. So that is why it is important for us to know how to determine the specific space area of the substances. Okay, now where are the applications of the BET space area? Now, the BET space area is applied in various fields, a lot of fields. Okay, for example, let me just change to laser pointer. For example, in batteries, performance of the battery component, for example, the anodes and cathodes, and also the separating membrane are affected by space area and porosity. And then you also have ceramics. Yeah, so the space area of the ceramics here will impact the sintering process, the thermal process, the moisture retention of the ceramic, and hence the product quality. And of course, I think a lot of you also are doing research in zeolites. The surface area and porosity of zeolites will influence the effectiveness of zeolites. And In pharmaceuticals, for example, okay, many pharmaceutical products are characterized by their BET space area to ensure optimal dissolution of the product, its bioavailability, and also cohesion. And of course, in powders for additive manufacturing, in the manufacture of carbon black, in metal organic frameworks. So all this utilizes the BET space area for one of their characterization. Okay, now let's take a look at some formula that you might have come across, when you were in school or high school, or maybe even now. These are some of the formula that your teachers might want our teachers might want us to memorize the last time. So you have the surface area of a cube, of a cylinder, sphere, and so on. Okay? So all these measurements, we look at these, are based on their geometric approach, meaning you look at the size, very specific size, and you use a formula, and then you calculate space area. But then this formula is not very practical when we do our research, in the sense that the products that we have can be in terms of powder form, it can be irregular shape, it can be porous, it can have sharp edges. So you cannot really use the geometric approach to determine the surface area of materials of this kind. The materials which we synthesize in our lab are more interesting, more interesting. So we need to have other methods of determining the surface area. So how then do we determine the surface area of these products, of these materials or our products, if you cannot use this geometric approach? So the approach here is to use gas absorption. Okay, so we're going to use gas absorption to determine the surface area. And in gas absorption, basically, we would like to know the amount of absorptive needed, okay, or the absorptive gas needed to cover the whole surface. So we have a material, we expose it to an absorbent gas, and the absorbent gas will need to cover all the spaces of our material. And from there, we determine the specific space area of that particular material. We use the term specific space area because it is per gram, so it's meter squared per gram. So we use the term specific space area. So we are talking about gas feed absorption. Yeah, we talked about feed absorption the last time in Bicara Pakar. So just to recap, it is an experimental technique based on equilibrium van der Waals interaction, because we're talking about feed absorption. So the interactions are mainly van der Waals interactions between the gas molecules and the solid particles. And we quantify that to become this specific space area. And beside this specific space area, you can also get pore size distribution, pore volume of the solid powder as well from gas absorption studies. So these are the outputs from your gas absorption studies. You will basically have a relative pressure over P naught and the volume absorbed. So basically in the gas absorption, you're going to pump in the gas, increase the pressure, and see how much volume is being absorbed by your material. And from this output here, and knowing the weight of the sample, you are going to get results on the pore size distribution, the pore shape, pore volume, and of course the specific space area. So today we'll focus on this specific space area. So all coming from the gas absorption analysis. Okay, now before we move on to the historical development, I have one very short question. Yeah, Ain, can I just throw one question to the audience? Yeah, Ain, I can give one question so you can answer in the chat, right? Okay.
Okay, can Doctor.
All right. Okay.
What
That's the term. What does the BET stands for? What does the abbreviation BET stands for? So you can answer in the chat. Oh, I see answers there. Let me see if I can check. Oops, I can. Bruno Emmett Taylor. Okay, Embly 2. Okay, that's the right answer, Ain. So we have a winner there, Embly 2, right? She's the first one to answer, she or he? Not sure. Bruno Emmett Taylor. Congratulations. So Ain, you take note of the name, right? Okay, all right.
Doctor. Thank you, Emily.
Okay. All right, let's take a look at the historical development. Now, I enjoy looking at the history of development of methods, just for the fun of it, just to see how people think, yeah. One of the book which I enjoyed reading when I was much younger is by Richard Feynman. Yeah, Richard Feynman is a Nobel laureate. He's a physicist. If you like to do research, if you like to read about, how discoveries have been made, Richard Feynman from Caltech University, he worked in Caltech University. He's one of the, it's a good read lah. I think I have read about three books regarding Richard Feynman and his work. Yeah, so it's a good book to read. It can give you some inspiration. Not previously, so many years ago when I was younger, I gave it to my undergraduate students to read. Dr. Saufi, he's now a lecturer, and also Dr. Amy, a few of them to read just for the fun of it. Okay, so let's take a look at the historical development. Okay, now this is Irving Langmuir. Okay, Irving Langmuir was awarded the Nobel Prize in 1932 for his investigation concerning surface chemistry. Now, when we talk about gas absorption, we're talking about surface chemistry. In this case, we are talking about the interaction of the gas and the solid surface. So the Laminar model was originally developed to describe and to quantify absorption of gas molecules on a set of distinct localized absorption sites. What this means is that you have a solid surface, so you have a localized absorption. Okay, once the sites are occupied, the molecules no longer interact with other molecules. Okay, so basically, the Langmuir isotope model is based on three primary assumptions. Now, all these models, be it Langmuir model or Freundlich or Bett or Temkin or whatever models that we have, they have their limitations. Okay, they are based on mathematical equation. They have their limitations. Okay, so the assumptions are the solid surface is made up of a uniform array of energetically identical absorption sites, meaning to say, which is not quite true, right? Because we know that our samples are mostly heterogeneous. Now, the assumption is that they are uniform, they are homogeneous, and the surface is energetically the same, meaning the heat of absorption is independent of surface coverage. So that's what they're saying, okay? And then based on the Langmuir isotherm, one very important assumption is that Langmuir assumed that there can only be a maximum of one monolayer, meaning to say only one adsorbate molecule can occupy per site. Once the site is occupied, absorption no longer takes place, right? So the Langmuir isotherm assume that you can only achieve up to a maximum of one monolayer, right? And lastly, there's no interaction between the adsorbed molecules, no interaction between adsorbed molecules, and the absorption is localized, meaning the adsorbed molecules do not interact laterally. They only interact between the solid surface and the gas, yeah? For example, between the adsorbent and the adsorbate. No lateral interaction between the adsorbed molecules. So and then came these three handsome guys. Yeah? So we have Stephen Brunner, Paul Hugh Emmett, and also Edward Teller. So they published a paper in February 1938 entitled Absorption of Gases in Multi-Molecular Layers. So before this, Langmuir said that absorption can only take place in a monolayer, right? So once it's filled up and full stop, yeah. But these three gentlemen did a study and found that you can have multi-layer formation in absorption of gases, in gas absorption. So if you look at the physical absorption process, a schematic diagram of it, I took this from the Micromathematics website. Yeah. So the physical absorption, let's say for example, this is your adsorbent, yeah, adsorbent or the solid, not adsorbent, solid, sorry, solid. And these are your gas molecules, assuming these are your nitrogen molecules. So at a pressure P1, for example, once you increase the pressure, the molecules will they are chaotic moving based on the kinetic molecular theory of gases. The gases are moving chaotically with high kinetic energy, and they will absorb spontaneously on this surface. Okay, absorption is a spontaneous process. Okay, and of course, when they absorb, the entropy change will be reduced, a negative entropy change. And then as the pressure increases, so P2 is greater than P1, you're going to have more molecules on the surface, and at any given time compared to the number of surface at lower pressure. So the greater the pressure, the more molecules are going to be absorbed onto the surface of your solid. Finally, okay, you have the formation of the monolayer. So a monolayer in this case, for example, all desorption sites are occupied. So based on the Langmuir theory, once it's occupied, you no longer can have any more absorption. This is based on the Langmuir theory. But then according to the BET theory, you can have multi-layer formation after this. Okay. So the motivation of proposing this multi-layer is the fact that they have evidence of the existence of multi-layer absorption, and also on the layer polarization theory, which is inadequate. So the BET model here states that, so this is your first layer, the free surface, sorry, this is the free surface, unoccupied site. You can have surface S1 here, which are occupied single here, and you can have S2 and also S3. So you can have single layer, you can have double layer, you can have triple layer, and you can have infinite layers. So this is according to the BET model. So the BET model actually is an extension of the Laminar model. So the BET model still assumes the same thing like what Laminar model assumed, but except that BET says that you can have multi-layer absorption, and it involves condensation, yeah, or liquefaction of the molecules. Okay, the main difference will be allowing condensation of previously adsorbed molecules. So this is difference between the Laminar model and the BET model. So the BET model allows multi-layer absorption, whereas the Laminar models assume a monomolecular layer absorption. Okay, so these are the assumptions. The same assumption as that of Laminar, but allows the multi-layer absorption. All the absorption sites are energetically identical, same like what Laminar model is. Now, the heat of absorption, delta H of absorption, is only for the first layer. So if I can go back, yeah, so the heat absorption will be involved between the first layer and the surface of the solid material only, right? Subsequent layers are basically your delta H of vaporization. So basically, when you have absorption, you're actually talking about the liquid state, yeah, rather than the gaseous state. So the heat absorption or delta H absorption for the first layer has a value determined by the properties of the surface and the adsorbate. So it depends on the nature of your surface, whether and also the nature of your adsorbate gas, yeah, whether the interactions are strong or weak. That depends on the properties of your surface. But for the second and all subsequent layers, it is equal to the heat of vaporization of that adsorbate gas. So for the that's why for nitrogen, for example, the experiment is run at 77 Kelvin, which is the condensation temperature of nitrogen, liquid nitrogen. Fourth assumption, the lateral interaction of adsorbed molecule is negligible. They do not interact, yeah, laterally. The rate of absorption is equal to the rate of condensation on the preceding layer. So the second, third, fourth, and layer, okay, the rate will depends on the rate of condensation, yeah, of the gases. And at the saturation pressure P0, the number of layers are infinite. Unlike the Langmuir, they assume that, one monolayer and that's it, right? But at the saturation pressure of P0, P0 is normally taken about 1 bar. So your relative pressure P over P0 is about 0.99 or about 1, yeah, but very close to 1. Okay. So at this saturation pressure, the number of layers are infinite. You can have many, many layers. So this is also a schematic diagram to show you, okay, this is the first layer, right? And then you have the second layer, third layer, and the fourth layer. So the molecules in the first layer will act as site for the molecules in the second layer, and then these molecules in turn act for sites of the third layer and so forth. Okay? No lateral interactions are allowed. Yeah. So all the layers above the first are assumed to have a liquid-like property. So all these layers above are all in the form of liquid, right? Okay. Now where? Oops, I'm trying to move this thing. Okay. Okay. Previously in Bicara Pakar, we talked about physics option isotherms. There are the 6 types of the physics option isotherm based on the IUPAC classification. But where is the BET equation applicable? Right? So we always run our BET equation, sometimes we do get good results, sometimes we cannot get any results, we get very low species and so on. So basically, the BET equations are only applicable for a type 2, which are dispersed, non-porous or macroporous solids, and type 4, mesoporous solids, which is the point diameter between 2 to 15 nanometers. So the shaded area here are the BET range. The classical BET range is between 0.05 to 0.3 relative pressure. So you have a plot here, P over P naught, this is the relative pressure. The maximum P over P naught is about 1, yeah, 0.9 or about 1, right? And this is the number of moles absorbed or the volume. Can have in terms of number of moles or in terms of volume. So this is the BET range in which the BET model is applicable. And it is strictly not for microporous material. So in this case, you might not get a purely type 2 or purely type 4. You might get a combination of type 1 and type 2 isotherm, or a type 1 and a type 4 isotherm. So be very cautious of that of the presence of micropores. Now we know that most of you have who, for example, have worked with determination of space area knows that if you have micropores present, you have to do the alpha S plot or the T plot to determine the micropore area. You cannot get it from the BET space area. So, once you look at your, let's say, for example, you have a combination of type 1 and type 2 or type 1, type 4, you have to look at the pore size distribution, the BDH, desorption pore size distribution, and from there, you have to run the alpha S plot or T plot to determine the micropore volume and test the micropore area. You have to take into consideration the S bed and S external, and then minus to get the micropore areas. So that is another one. You cannot get directly from the BET space area. But of course, even though it is not strictly for micropores, there are some guideline to use here. For example, I should just now get the alpha S and a few more. I will talk about it afterwards, right? Okay. Oops. Okay. All right, calculating the bed space area or the BET specific space area. So these are the formula that most of you are maybe are commonly used to, right? So these are the two forms of the linearized bed equation. So you can have it in terms of the number of moles or in terms of volume. Okay, so these are the linearized bed equation. It is the form of y equals to mx plus c. Yeah, so this is c, the y-intercept. This is m, the slope, and this is your x. Yeah, this is your y. So the p here, yeah, is the equilibrium pressure of the gas. Yeah. Now absorption process is always an equilibrium process. Remember we discussed the last time. The absorption process, the gas phase absorption process, is always an equilibrium process. Yeah. The system must reach equilibrium. You have adsorption and desorption. Yeah. And P naught here is the saturation pressure of the gas, approximately 1 bar. N here is the quantity of gas, number of moles absorbed at pressure P. And M is the monolayer capacity, which is the quantity of gas in terms of mole absorbed when the entire surface is covered with a monomolecular layer. Now, even though we say that the BET model or the BET space area equation in the BET model take into consideration multi-layer formation, but then when you determine the space area, you are still looking at the part whereby the monolayer coverage is complete. For example, if we look at, if I just can go back to this one, yeah. Okay. This region here, okay, you have a point B here, point B here. This is the point whereby the monolayer coverage has been completed, and this is the range which you take to calculate the BET space area. You cannot take the whole range of your P over P naught relative pressure, because when you talk about space area, you are still talking about the monomolecular layer, right? So even though you cannot you are talking about multi-layer coverage, but when you talk about the BET, you're still talking about the monomolecular layer coverage. Okay. So that's what we have here. Nm, which is the monolayer capacity, quantity of gas in terms of amount of moles absorbed when the entire space is covered with a monomolecular layer. Or you might want to use the formula in the form of volume. Yeah, okay, sorry. The C here is a bed constant, which is related to absorption energy at the mono layer. V is the molar volume of the adsorbate gas at the specified equilibrium pressure, and Vm is the molar volume at the monolayer coverage. So this is the most common linearized. This is the linearized by equation that we use. Some people prefer the one with number of moles, some prefer with the one with volume. You can use either one. Okay. Now, for many absorption systems, the bed constant C is related to the heat absorption, which is the first layer, delta H absorption, and also the heat of liquefaction. Yeah, so it is related to the heat absorption between the first layer and also the second layer. So this is the exponential of the H1 minus H2 divided by RT. And the value of the bed constant is very important. It actually indicates affinity of the absorbed molecules for the solid surface. A high C value indicates a very high affinity between the solid surface and the absorbent gas. Yeah. A low C value indicates a low affinity between the solid surface and the absorbent gas. If you're talking about nitrogen, the typical C value will be between 50 to 300. Yeah. And a high C value also actually is an indication of the presence of microporosity. So if your C value is very high, more than 300, then there is a possibility of having micropores in there. So you go and have a look at your desorption, BGH desorption, to see whether you do have micropores or not. If you do have, then you have to run the alpha S plot or the T plot. So this is a comparison of a graph of N over Nm, yeah? The number of moles versus number of moles at the monolayer coverage versus relative pressure. So these are the values of C, yeah, for the different for the different plot. Yeah? So over here, if you look at the first isotherm, yeah, A, the value of C is 1. Okay, so this is like more to macropolar substance. Yeah? And then if you go to the second B here, the C value is 11. The next one, C, the C value is 100. And D, the C value is 10,000. If you look at the way, if you compare between the D isotherm and the A isotherm, this indicates the presence of micropores because you have a very high intake at very low pressure, and you also have a knee here. Right? So basically here, this might be a type 1 plus a type 4. If you can see the hysteresis loop, then it might be a type 1 plus type 4, or maybe a type 2. Right? So some of the literature also indicate that the values of this bed constant can also tell us roughly the shape of the isotherm, whether it is a microporous combination with mesoporous or a non-porous. Okay, and also if you get a negative C, then something is wrong with your range of coverage of the bed, or maybe your sample is too small, or maybe your sample is not suitable for the BET surface area analysis. Okay, so now how do you calculate the BET surface area? Right? Normally, what we do here as students, normally they will prepare the sample, and then they will send to UIRL, or they will send it to the Department of Chemistry or wherever here in UTM, which has the BET surface area analysis, and that's it. Okay. So what you have to do, what basically the technician or the pegawai science, science officer do with that, they will run the analysis, on gas absorption analysis, and from there they will obtain the phase absorption isotherm. This phase absorption isotherm will have to be transformed into the bed transformation plot. Just with the phase absorption isotherm is not enough for you to determine the BET space area. You have to transform it into the bed transformation plot. And all of this, of course, is done by the software. You get your how many pages of that data if you run the multi-point analysis. Yeah? And from that, you get the value of the BET, monolayer capacity, and M. And in the second stage, the bed area is calculated from NM or from VM by adopting an appropriate value of the molecular cross-sectional area, sigma of the adsorbate gas. So if your adsorbate gas is nitrogen, you have a specific molecular space area, cross-sectional area. If you're using argon or krypton, then you have that value for the molecular cross-sectional area of the gas. So you need to run the phase absorption the gas absorption, and then you transform it to the bed transformation plot, get the monolayer capacity NM or VM, and then from there, you calculate the bed surface area. Okay, now this is the bed transformation plot that we talk about, which uses the bed equation, BET equation. So we plot Y, this is your Y, yeah, versus X, which is your P over P naught, and C minus 1 divided by VMC is your slope, S, and your VM, which is the intercept at the Y-axis, is equal to 1 over I plus S, the intercept plus the slope. And the intercept here is equal to 1 over VMC. So from here, yeah, you can determine what is the molar volume. You know the slope from here, you can also determine the C, yeah, once you get this. And notice that the bed transformation plot only takes between 0.05 to 0.3 range of P over P naught. Even though you run the isotherm up to a P over P naught relative pressure of about 1 or 0.99 and so on, but when you run the bed transformation plot, you only take data in the range of 0.05 to 0.3. This is the classical bed range. But still, you know, sometimes you need to push it a bit lower depending on your sample. This is a classical range. Yeah? Okay. Now, linearity does not apply to whole range of P over P naught. Yeah. If you go outside, then it's no longer linear, right? Then you will not get the correct. You will not get the correct or accurate answer for your BET space area. So it's between 0.05 to 0.3, not negative 0.5. This is between 0.05 to 0.3 P over P naught. Okay, so this is just a bit on description of the the isotherm. So this is the linear range, and this is the monolayer absorption, yeah, which is being covered here, right? We do not take other ranges of the P over P naught. We only take between 0.05 to 0.3. Okay, and of course the micropore filling also takes space here. So if your sample has micropores, that's why you have to be a bit cautious when you determine the BET space area. All right. So most of you, I think, when you go to UIRL, you will send your sample, and then they maybe will run a single point bed space area, maybe, right, as a start to see whether your samples, what are the range of your space area. In companies, for example, if you want to have very quick data on the BET for the next course of action, they will just run a single point bed space area, right? But then the multi-point bed space area is more accurate. So the multi-point can involve 3-point bed, 5-point bed, or the 10-point bed space area. Okay. So if you just have a look at the filling, the pore filling here, just to show you, this is the micropore filling. So you notice that the micropore filling, basically the micropores are very small, less than 2 nanometers. So they automatically fill up, yeah. And then you start the multi-layer filling and so on. And this is your saturation. This is your pore condensation, whereby the hysteresis loop. And this indicates the saturation pressure. And this is actually where you can determine your pore volume. This is another view of the explanation. Okay. All right. Okay. Now we look at the specific space area calculation. Ain, all the questions kita akan jawab. We will answer it after the talk, right? Or do you want me to answer now, Ain? After the talk.
I think after the session finish.
Okay,
After the talk.
Right. So everybody is clear, right? So we need to first run the gas physics option analysis. From there, we will transfer it to the bed transformation plot. From the bed transformation plot, we'll get the VM or NM. And from there, we are going to use this formula to calculate the surface area. So this is a very general formula. Yeah. The surface area of the solid can be determined by measuring the amount of particular gas absorbed, yeah, your VM or your NM, on the surface with known molecular cross-section area of the adsorbate gas. So in this case, the VM is obtained from your bed transformation plot, multiplied by the cross-sectional area of your liquid, of your nitrogen. This is from nitrogen if you're using nitrogen as the adsorbate gas. This is your Avogadro constant, and divided by the volume at STP. So this is the generalized surface area calculation if you're using nitrogen as adsorbate gas. If you're not using nitrogen, then this value will change. So the value 4.35 will also change, right? So most often in our sample, we use nitrogen as the inert gas, as adsorbate gas. So most often the student will use this formula here for the calculation of the specific surface area in meters squared per gram. Okay, how do you prepare for your sample analysis? Okay, of course you do your sampling. Now remember, the amount of sample you put in for the analysis is not much. How many grams normally iron? Maybe less than maybe 0.1 gram, 0.5 grams, not much. It depends on your sample also, okay? It's not much, okay? The sample mass basically between 0.5 to 2 grams, it depends on surface area. If your surface area is about 5 meters squared per gram, you need between 2 to 3 grams and so on. Okay, these are just a guideline which is being suggested by some of the instrument supplier. See, these are just some of the guidelines. Okay? And then, of course, when you take your sample, you must remember that you have a bulk sample. Make sure that your sample is homogenized when you take. It must be representative of the sample, so that you can get the correct, a more accurate result for your surface area. Okay. Sample preparation. This is when you run the sample, and of course, when you run the sample, the science officer will ask what is the degas temperature that you would propose. Yeah. So the temperature. The degas temperature is a very important factor. Yeah, I will show you the effect of degas temperature. How long does it take? Are you going to a vacuum or inert gas flow in the sample preparation when you degas? Yeah, and the setup. These are all being done by the pegawai sign or the science officer or by the technician. Yeah, the absorptive gas instrument, so on. Instrument, the one that we have in UIRL or in the Department of Chemistry, we have the micromagnetics Assoc 2000 or something, I can't remember the numbers. And of course, there are other instrument brand, which have a slightly different setup, but the formula is still the same. And of course, the analysis parameters. Yeah, so very important is sampling. Make sure that your sample is representative of your bulk sample. If your sample is not representative, then you might not get an accurate sample. And the sample mass, this is just as a guideline. You will know from your experience, how much you need to use. Yeah. Okay. And of course, different instruments sometimes have different way of doing it. So normally the lab technician, they will also refer to the supplier of the instrument. Okay, so this is example which I took from the micromagnetics website. Yeah, example of a mesoporous silica alumina. So if you look at this mesoporous silica alumina, what they did is that they did two ways. They did the isotherm linear isotherm, and then from there they run a bed space area. Okay. Another one, they did just a 7-point bed. This whole thing is the whole isotherm. Right? They run the whole isotherm and then they run the bed space area plot. In another way, they just run a 7-point bed, and then from there they get the bed space area. So if you compare the data that they get here, if you run the whole isotherm, up to P over P naught relative pressure about 1, and then do the bed transformation plot, the mass, let me say, comparing both masses are the same. They use the both mass for the same, for both methods, 0.23898 grams. But in the first part here, whereby they run the whole isotherm plot and then run the bed space area in the range of 0.05 to 0.3, the surface, the aspect is 203.56. But when they did with a 7-point bed and then run the bed transformation plot, they get about 203.35, which is about the same. Very important, the R squared is 0.9. This is not R, it's R squared. 0.999. This is also 0.99, which is good. You want to have a 0.999, yeah, R squared, correlation coefficient. The C value is a bit different, 129.89. This is 142.78. But the molar volume is about the same, 46.72 and 46.77, right? So both method, whether you run full blast, up to relative pressure P over P naught up to 1, or you just take a 7-point bed, you get about pretty good BET space area for both methods. So in this particular case, both methods are okay. So you don't have to run the whole custom plot because this will save time, right? Okay. Oops. And then another sample that they show is for zeolite. Let me just show the whole thing first for the zeolite. As you know that zeolites are microporous substances. Yeah. So if you look at the isotherm here, the linear plot, yeah, it doesn't give, if you took the linear plot from 0.05, yeah, we're talking about 0.05 to 0.3 only, it's sort of, it's already saturated, right? You do not see any changes here because they run it from 0.05 to 0.3 relative pressure. So it looks like just an isotherm linear plot, just show this. And when they run a back transformation plot for this data from 0.05 to 0.3, they get a negative C, minus 36.45. And this is impossible. Once you have a negative C, then your data, you cannot use your data. And the SPET 766.31 is no longer reliable. And if you look at the R squared, it is 0.9958. It's not 0.9999, it's 0.9958, right? And the molar volume here, VM is 176.06 centimeter cube per gram at STP. So again, this here, minus 6.5, indicates that your data, the range of data taken here is not applicable. So remember, zeolite is a microporous substance. So when they run the full plot, they realize that, they notice that, of course, when they run the full plot, it is a microporous substances. And this particular range is already the saturation limit. So that's why you do not get anything when you run point between 0.05 to 0.03. So you might want to run it at a lower pressure, or you might want to do few other modifications in this case. Okay, isotherm is already saturated in the classical BAT range. So in this particular case, yeah, sorry. In this particular case, you might, okay, you might want to run the sample at a lower pressure, between maybe this lower pressure. Or what they did for the micromagnetics, they run on another instrument actually, which caters for the microporous area here. Okay, we're just showing you that if you run, what I'm showing here is that example of if you do microporous material whereby the BET equation is not applicable, you're going to get a negative C. And if you look at this here, this is already saturation limit. So you need to run probably at a lower range rather than this range. Okay. But in that case, in the case of the micromagnetics, they run in another instrument and they do some modification with the data to get the microporous area, space area. And then another example is of a polymer. So if you look at the isotherm plot between the bed range, they only run the isotherm plot between the bed range of 0.05 to 0.3. If you notice that it has the isotherm increases, decrease a bit, and increase a bit, right? There's rightfully, as we have seen earlier, if you increase pressure, the volume uptake should increase. Remember, when we look at our earlier schematic diagram, at P1, you have absorption of gas molecules. And then as you go to increasing pressure P2, whereby P2 is greater than P1, you should have more gas molecule absorbed. But if you look at this isotherm, there is a decrease between 0. maybe 18 to 0.2 and an increment. Something doesn't look nice here, right? Okay. Now, when you look at the bed transformation plot from 0.05 to 0.3, the R squared is 0.9989, right? 0.9989. It's not 0.9999, it's 0.9989. And the S bed is very small, which is 0.2563 meters squared per gram. So one way of improving this data is to try to use larger sample mass in cases where you have very low surface area. So you have to make sure that this isotherm, number one, it has to increase with increasing pressure. You cannot have the isotherm decrease with the increasing pressure. If you have the isotherm decrease with increasing pressure, then something is not right. So in this case, they suggested that for low sample BET surface area, you need to use larger sample mass. Yeah, you have to make sure that your R square is 0.9999. Okay. Another example. Okay, wood sample which also with low surface area. Okay, look at the isoterm plot. They look only at the 0.05 to 0.3 range. It is decreasing, which is not right. The uptake should increase with increase in pressure. Right now you have it decreasing. Okay, and then when you run the bed transformation plot from between 0.05 to 0.3, notice the deviation from linearity beginning at 0.15. So what they did here is a 10-point. They did a 10-point bed plot here. So there is a deviation from linearity beginning 0.15 relative pressure P over P naught. So possibly what happens here, okay, there might be a leak. There might be an insufficient degassing in the sample preparation. Remember, in the sample preparation, you have to degas, right? You have to throw out all the impurities. There might be insufficient degassing. There might be a leak. There might be error in the free space. You don't have enough samples. Yeah. Temperature is not correct when you did the degassing. And insufficient equilibration. That means the samples have not reached equilibrium. Yeah, when the data due to maybe error in the free space or incorrect temperature. Yeah, because when you get the C value is okay, positive here, but then you have this decrease and deviation from the linear range in that region of 0.05 to 0.3. Okay, so this is an example. Okay, and then another example, I like this example actually for pharmaceutical. Notice that when you increase the pressure, the uptake decreases drastically. This is totally really not right. Yeah, very funny isotherm. And if you look at the bed plot, yeah, between 0.05 to 0.3, it doesn't resemble any of the bed transformation plot that we expect. No linear range whatsoever. Yeah, you look at the only between 0.1 up to maybe 0.15, and then the rest is, is very funny. So again, here checks for leaks, degassing, check for the absorbed gas. Maybe the absorbed gas is not suitable, right? Look at the surface area, it's 0.1696, yeah? The mass is about 1.1462 gram. R square is 0.9996. Yeah, C value is positive, okay, but still, this is not right. Okay, and the bed surface area plot, bed transformation plot is also not right. So you have to check for leaks, or maybe you have to change the absorbed gas. Okay, so what they did, yeah, with this particular sample, okay, let me just go back here. They use the same mass, 1.1462, but they changed the absorbed gas to krypton. So this is krypton, so it looks better. Yeah. This is nitrogen at the 77 Kelvin, krypton at 77 Kelvin. So the isotherm linear plot is better. There is an increase in the quantity absorbed with increase in pressure. This makes sense. This makes better sense. And when you run the bed transformation plot, yes, you get a point, it's still 0.996, but then you get a linear range, and the aspect is still small, but at least the isotherm is much better here. Did I get the same one? Or no, I think, I'm sorry. Okay. Yeah. So the data, oops, okay, you get a better bed surface area. So the point here is that when you get, the first thing that you need to see, the isotherm must, the amount of uptake must increase with increase in pressure. If you have it decreasing, then something is wrong. Check for leaks, check for sample, check for the temperature and so on, the gassing sample preparation. Okay. And then when that is okay, then run the bed surface area transformation plot. If you get a negative C, then something is also wrong, which you need to check. Otherwise, if you get a straight line with correct, with the right 0.999996 or 0.999, preferably 0.999. But in this particular case, since you have, this is the best, at least you get a linear ratio, then it's okay. Okay. Now, what is the effect of temperature on the degas? So we have looked at examples of isotherm plots and the bed transformation plot using 7-point, 10-point, and the normal, the full range of the multi-point bed plot. Yeah? We have seen some of the concern here. So if you look at the degas temperature, comparing the gas temperature, In this particular case, we have 4 samples. This is your carbon sample, yeah? CM350, CM50, CM150, and also CM250. This is the degas time for 30 minutes. You're using at different temperature, yeah, at 50 degrees Celsius, 150, 250, and 300 for the same sample. And notice the resulting space area. So you might want, if you are really not sure about a sample, you might run to see the effect of the gas temperature on your surface area of your sample. Okay, these are variables which you can run and see which would best give the surface area of your sample. Right, so because the temperature of the degas will have effect on the resulting surface area. So this might be one variables that you might want to study if you're really going to run on this surface area, something which you might want to consider studying. But of course, most of the time, yeah, the student will send the samples and they just like, okay, this is the degas temperature, full stop. And then most of the time, the science officer will ask, have you looked at the literature? What is the suggested degas temperature, and so on. Otherwise, you might want to consider studying the effect of the degas temperature on your sample surface area. All right, okay. Problems that you might face in the BET measurement, surface area measurement. If a straight line is not obtained, if you don't have, the correction coefficient is worse than 0.999, if there's a negative intercept, okay, these are the things which we discussed just now. What are things which you should do, okay? If you have C above 200, indicative of presence of micropause, and when we have micropause, be very careful, yeah? You need to do the alpha S plot or the T plot, yeah? If it's below 100, this may indicate very strong adsorbate interactions, yeah? It must indicate, not strong, indicate weak, yeah? Adsorbate interactions. Sorry for the typo there, okay? And solutions to some of the bad problems, yeah? If you have a very small sample area, your nitrogen adsorbate might not be suitable. You might change to another adsorbent. Krypton is quite actually suitable for small space area samples. Yeah. For example, maybe your filler rods or the glass spheres are not suitable. Yeah, you might want to change that. Okay. Or you can have very small amount of sample available. Yeah, so maybe this leaves you very large dead space. So this can be addressed by using maybe filler rods, spheres, or to reduce the dead space in your sample. Okay. Or maybe you can also have difficulty achieving the straight line. These are the issues that we discussed just now. Yeah, the range are possible not linear. So you have to look at back at the range and see whether your samples are consistently prepared or analyzed. Yeah, degassing and so on. So these are common issues. Yeah, related. Yeah, sometimes one of the issues sometimes is degassing. Yeah, sometimes some sample takes a very long time to degas. So you have to look at how you prepare your samples, yeah, things like that. Okay. Okay, and then how do you report your BET space area data? Make sure that when you report your BET data, yeah, this is taken from this report, yeah, reporting physics option data for gas solid system with special reference to determination of space area and porosity. Make sure you note down what is the model of equipment used, what is the pre-treatment and outgassing condition, what is the mass of the outgas sample that you use. So note down, yeah, because different instruments have different specification. Okay. Adsorptive gas use, using nitrogen, krypton, or carbon dioxide. Yeah. What is the, when you report on the bad data, report on the specific space area, report on the C constant, report on the correlation coefficient, report on the temperature. And then maybe you have methodology data, uncertainty data. Maybe you want to do a few measurements and run on the, for example, statistical analysis. If you can run more than one. Yeah. Normally, we would suggest run at least 3 samples for the same sample, you run 3 times and then you get an average of it. Okay. But the very first thing that you need to consider is that you have to make sure that when you do the sampling, the sample is representative of your bulk sample. Once the sample is not representative of your bulk sample, then everything else is gone, you know. In any analysis, the sample must represent your actual sample. Okay. Right. I'm just going to stop you for a while to look at some question, because over here I have actually prepared slides. If they, you know, if the audience would like to know on the adsorbate gas here, which are being used here, I took it from this person's slide, yeah, on the characteristic of powders and porous materials from this person. You can just Google and can get the slides, quite good slides, yeah, which discuss also on the common adsorbates, why different adsorbate will give different areas, yeah, different surface areas, right? Maybe we can look at this later if we have time. Do you have time to look at that? I have quite a number of slides on the adsorbate gas, but never mind. Maybe if you need to know about that, maybe you can spend a bit of time, maybe 5 to 10 minutes on adsorbate gas. Otherwise, I will look at the question first. Ain?
Okay, Doctor, thank you. We have about 13 questions actually.
Okay, let me stop sharing. Stop.
Okay.
So let me hold on. Let me stop sharing automatic and stop.
Question question number 1. How much for BET and for size distribution analysis? Hey, Doctor, can you hear me?
Oh, I'm on mute. Okay, all right.
Doctor?
Sorry. What was the question, Ain?
Number 1. How
Uh-huh.
much for BET and for size distribution analysis?
That is the cost. Do they want to know the cost or what? The cost, I
cost or
think I will answer that. The cost. How much you're thinking about, the cost or the amount? The amount will depend on your sample. That's why sometimes, for example, if you have a very bulky sample, like wood sample, you cannot put so much in the sample holder, kan? So maybe you can start with like 0.2 grams or 0.5 grams as a start, you know, and then if your surface area is very small, you have to increase the sample size. It's actually also based on, look at the literature if you have a similar sample, and also based on the experience of the science officer, lab technician who runs the sample. They are very good source of reference, actually, the technician and then science officer who runs the sample. But normally about maybe 0.2, 0.5, depending on your nature of your sample.
Okay, the question number 2, I think the same question as before. So I go on to question number 3. How to determine the gassing temperature of a material?
Okay, this one, honestly, you have to look at the literature and look at the proposed, the suggested degassing temperature for example. Normally, UIRL, what will be the temperature that you would propose in general? Because some samples you cannot have very high temperature, because that's when we see that different degassing temperature will have different effect. 100 degrees, 150 degrees Celsius, 60 degrees Celsius. It really depends on your sample. That's why you really need to know that, you really need to have that data to give to the lab assistant, the lab technician who runs the sample. Only you would know best on your sample. That is why I would suggest, if you have time, you have lots of sample, run the effect of the gas temperature on the surface area. That would be good, you know.
Okay. Next question. How do you relate BET and density of the sample?
How do I relate BET? Okay. Density is mass over volume, right? The surface area is meter squared per gram. I'm not too sure. When we talk about density, it's like how many grams per centimeter cube. But when we talk about space area, is what is the area meter squared per gram. So is there a direct correlation? It depends. If you have a very porous material, the surface area can be very large, but it is less dense. Okay. For example, if I work with a porous material, what was it? This pumice rock. I worked with once a long time ago. It's very lightweight, but it has very high space area. The bed space is very high. So if it is very porous, very high space area because of the porosity, then the density will be very low. That is one thing which you can relate, because it is very lightweight, but it has a very high space area. So you can actually also indicate that very high porosity can have very low density, because the mass is very small because you have very porous material. Yeah. Okay.
Okay, next question, Doctor. How much is the ratio of accuracy compared to geometrical equation?
Oh, it's difficult to say because if I have a cube, I will use the formula to run to determine space area of the cube. But my samples are not perfect cubes, for example, right? It can be different irregular shape. So I cannot compare the ratio of the accuracy compared to geometrical equation, because when you talk about gas option, the gas, you expect the gas to cover the whole surface, internal and external surface. Remember, the particle, the materials have pores, so they have internal space area as well. When we talk about geometrical, I doubt you can know the ratio of accuracy. I'm sorry, from ikhlas here. I'm not sure about that. I don't think you can relate the accuracy to geometrical equation.
Okay. Next question, Doctor. How to determine the duration of the gassing process?
Well, until all your because I remember at one time, in Department of Chemistry, the lab assistant told me, Doctor, sampel doktor ni satu malam pun tak boleh digas, because you have to reach the vacuum kan, a certain pressure. So it depends on your sample, honestly. Somebody in dalam ni ada from URL, if you can share how long it takes for you to degas certain samples. Anybody can share? Zubaidah, who runs the surface area analysis, Ain? If they can share?
Poliana.
Poliana, ya? How long does it take normally, Liana? It depends on sample, right, Liana?
Maybe she don't have the speaker, Doctor.
Oh, she doesn't have a speaker. Okay. Degassing depends on sample. Even temperature also depends on, but you must remember the degassing temperature must not decompose your sample. That is why I mentioned earlier, refer to the literature, refer to the past, maybe your past researcher, or your supervisor have other students who have done this before. Refer to that and see what is the best degas temperature. But it must not decompose your temperature, decompose your sample, and the time will depend on your sample. I remember, that's why just now I remember, the lab assistant told me, doktor satu malam pun tak boleh digas kata. You have to evacuate everything. Yeah, degassing basically you evacuate. So you get the lowest pressure kan, almost a vacuum, right? So you have to do that. So it depends on temperature. So sometimes that's why they will ask you to dry your sample first, make sure your sample is dry and then send for degas. Yeah.
Okay, next question, Doctor. Based on TGA result, what is the suitable temperature to be used as a reference for the gassing temperature? Is it the starting temperature?
TGA. Okay, when you run the TGA, look at the temperature where your sample will start to decompose. So don't do that. You have to go below the decomposition temperature of your sample. Okay, let's say for example your temperature starts to decompose at 150 degrees Celsius. So do below 150 degrees Celsius. Okay, do below that. Because if you do at 150 degrees Celsius, then your sample would have decomposed already.
Okay, next question, Doctor. During T-plot customization, I found there is a different type of thickness. Curve equation, for example, Hawkins and Jura.
Okay.
I think it's
Hawkins, Jura, Birkenbauer, and
yes,
alright, okay.
and carbon black star.
Yeah.
Do
Okay,
you
then
have the rule?
okay. Because if you look, I normally use Hawkins Jura because the thickness I think is, I can remember thickness range. I normally, oops, hold on. I have a class now. Okay, there are, you have to look at the thickness. Each of these T-plot, yeah, T-plot equation for the in order to determine the thickness, statistical thickness, have its range. I normally use Hawkins Jura. So I'm not sure. I'm so sorry. I do not have a rule for that because my samples, the Hawkins Jura works best for my sample. I'm so sorry. I'm not very familiar with the others. But of course, there are different equations. Yeah, the Debye equations, Hawkins Jura, and so on. But I honestly do that for the Hawkins Jura. Still, yeah, maybe the others in the audience can answer that. I'm really sorry. I'm not too familiar with others. I'm familiar with Hawkins Jura, statistical thickness before you run the T-plots.
Okay, Doctor, next question. Any other method to determine the surface area without using BET?
Meaning you don't want to use gas absorption?
I think so. Without
Okay.
using the BET, the alternative one.
Most of it, for example, even if you have DFT, you still need gas, yeah? Other samples, because if you run the gas absorption isotherm analysis, they have a few options, yeah, to run the surface area plot. So if your samples, for example, well, still, if you can use there are other methods. So for example, you can use from your DFT calculations. You can use from the pore size distribution, from the SEM. You can also do that, yeah. I have actually a slide there on the different types of different methods here for the PSD. You can also use the space area for that. The DFT, you can also determine the space area, yeah, besides the BET space area. A few more, even from your SEM, you can also determine space area actually. But there are a few other methods besides the BET space area. Yeah, exactly.
Okay, Doctor, another question. Is it possible if the size of particles is too small, the isotherm line increases and the reading of BET plot becomes scattered? The size is small.
Meaning?
The particle size is small, but the isotherm line increases and the reading of BET plot becomes scattered.
Okay, you mean between the classical range of 0.05 to 0.05 to 0.05 to 0.3? Yeah, possible. So in that case, sometime maybe your absorbed gas is not correct. You might want to change to absorbed gas. You might increase the sample. You can check for leaks and so on. Possible. It is possible. In fact, the micromagnetics have an instrument which they call Gemini. I'm not familiar with the Gemini, but for samples like that, whereby there's increase, but the BET plot gets scattered within the range, they have to do a different plot so that they can get a good BET transformation plot. So it is possible actually.
Doctor, the 12th question. What is the difference between BET surface area and AFM measured topography?
What is the difference between?
Between BET surface area and AFM measured topography. AFM.
Yeah, I know. Atomic force microscopy measured. Okay, the BET space area is based on gas absorption. Okay, whereby the absorbed gas covered the external as well as the internal surface, right? When we talk about AFM, we're just talking about the topography on the surface only. So, but the BET covers all the internal as well as the external space area because you're talking, it is based on gas absorption. But the AFM topography is based on the surface analysis. And there is a difference.
Okay, this difference. Okay, another question. Assalamualaikum Doctor. I would like to know if there is any possibles of total pore volume is not equal to the sum of micropore volume.
And then
Example by T-plot and MP method. And mesopore volume by BJH method.
that, yeah. Um, mm, rightfully, yeah, when you have the total pore volume, you have the micropore and the mesopore, yeah, because if you have both, if let's say for example you have a type combination of type 1 and type 4 isotherm, you have the micropores and the mesopores. I'm not too sure. I've not have any experience with that. Rightfully, mathematically, it should be the total pore volume should be equal to the sum of the micropore and the mesopore, because you are looking at the same data, gas absorption analysis. It's just that one you are analyzing it using a T-plot, and the other one you're using the BGH for the mesopores. Rightfully, it should be the same. Rightfully.
Doctor, the 14th question. Is the degassing time has effect on the BET measurement?
Oh yes,
The
yes.
degassing time.
Yes, it has. Because that's why I think if you have enough samples, the variables beside the degassing temperature, the degassing time, those are the variables that you might want to consider and then optimize it for your samples. But of course, I know like sometimes our samples are not that much. So you just send it to the lab. You say, Kak, I want to analyze this, and then the lab technician will try to get the best temperature, yeah, based on the literature or maybe based on your TGA analysis, and then they run one sample and that's it, yeah. But if you could optimize it, look at the gassing time, look at the gassing temperature, then you might want you can optimize the surface area analysis, yeah. Then that would be better. But of course, we don't get, when we prepare a sample, we don't get that luxury of optimizing because you don't have much samples actually. And that sometimes certain samples, when you want to prepare a sample, it takes a long time. Then you get one sample, your very precious samples, and then that's it lah. Okay.
Hi Doctor. Okay, may I ask if there's any suggestion for high surface area sample around more than 30 milligram, like I have to reduce the is it I have to reduce the amount of sample?
Pardon? Suggestion for high specific sample around
Because
30,
sample is around 30 millisquare.
per gram. This one is not very high space area. High space area like 1000 ke 800, 700. This is not so, meaning to say for high space sample that I have to reduce sample amount. Tak faham.
Maybe the size is more than 30.
Subing, your space area is more than 30 meters squared per gram. You want to reduce the sample amount or you want it to be Subing can I don't quite understand. You said suggestion for high space area sample around more than 30 meters squared per gram. Okay, that's a new message there. I'd like to analyze nanostructure specific space area. Okay. All right. So you expect the surface area, because 30 meters squared is not a very high surface area actually, Subing, very low. So maybe in this case, you have to increase more sample, because if your space area is low, you have to use more samples. That is one of the recommendation. But if it's 30, if you get this 30 meters squared per gram, how much sample did you use, Subing? Oh, yeah, it's not high. I work with samples like activated carbon 1900, 800, that is high. But 30 is okay. It's not low, it's not high, but it's okay. Okay. Around sample treatment. All right, okay. So 1 gram should be okay. You can fit in the glass rod, which should be okay. But if you, let's say for example, if your space area is small, you need to use more samples. Yeah. But
I think
nanocellulose ni, they are not very, because my student work with nanocellulose juga. It is not very, you need to have more of it, Subing, for this one.
yes, Subing.
Yeah, okay.
Okay, another question also for Subing. Is there any minimum temperature the machine can go?
Okay, this one Yana have to answer. Yeah, the machine minimum temperature. You mean the absorption analysis?
Maybe the Yana already answer below. Depend on the sample and her temperature short time for the gassing.
No. They ask you. The question is there the minimum temperature for
Room
the
temperature. Oh.
Normally, it goes from room temperature to very high, like maybe from 25 to up to a certain temperature. Maybe Yana can answer that one. Yana, what is the minimum temperature? Yana, room temperature. Normally, it's from room temperature to. It depends on the instrument.
Okay, Doctor, the last one. Using the standard static
Okay.
heating method.
Ain. Minimum temperature more than room temperature. Okay.
Ah, that's the right answer.
Okay. Not below 30 or room. Alright. Okay.
The last question, Doctor. Using the standard static BET method, isotherm absorption, nitrogen desorption, the BET surface area of EFB biochar was
Okay.
measured to be less than 1 milligram, 1 meter cube per gram. Can
1 meter
doctor help
square.
me to
1
find
meter
a more
square per
accurate
gram.
method?
1
The
meter
last
square
one.
per gram. Yang mana dia punya soalan? Oh, this one. Using the standard static BT method, okay, alright, was the EFB empty fruit bunch biochar was measured to be less. Okay, I would suggest, how much, what is the mass that you use? Is that, if you have tried increasing the mass, if it doesn't work, then you have to, how was the isotherm, the increase ke, decrease ke, is that? When you get the isotherm, is it like a normal one, um, dia naik ke, turun ke with the amount of sample? Is that?
Is that you can unmute for a while?
Boleh unmute, is that? Oh, normal, it's increased, okay? So when you run between 0.05 to 0.3, the linear range too, what was the R squared value? What was the C value? Is that? Is it linear within the 0.05 to the 0.3 classical BET range too? Oh, it's linear, so it's good, yeah? Okay. So in this case, what you can do, try increasing the sample first. Try increasing the sample. Degassing temperature semua okay ya. Maksudnya degassing time, I would suggest first, try to increase the amount of sample first. If that fails, then you have to change to another absorbent gas. Krypton is good for very low space area ni. Krypton will be a good absorbent gas. Tapi UPMU tak ada kan krypton? Yang ada tak krypton?
Tak ada doktor, tak ada.
Tak ada kan? Oh, Zubaida, tak ada kan? Krypton tak ada. Tak ada krypton.
Okay, I think doctor you can go for the question for the quiz or you want to continue
Okay.
the presentation?
Okay,
Because we only have one just now already one question.
I
Only
want to ask one more
four.
question. I want to ask one more question. Okay.
Okay.
What does the value of bed constancy indicate? What does the value of the bed constancy indicate? Or what does the value of bed constancy tell you?
You can repeat again, doctor.
Okay, what does the value of the bed constant tell you? Or what does the value of the bed constant indicates?
This quiz number 2.
Okay.
Yes,
You can have more than one answer actually for this one. I will look at the answer and it can be more than one answer actually.
Okay, Doctor, maybe you can move on to your presentation.
Okay, just a bit on absorptive. Okay, let me share. Dah ada
Or you
jawapan
want to
tu?
check the answer first?
Okay,
Yes.
it relates. Okay, it relates to magnitude of the it relates to energy. And saya baca ya. It relates to the magnitude of the absorber interaction. Okay, which is betul, Emily. Magnitude, that means you're talking about the how strong or how weak the interaction between absorber. This is okay. Energy absorption of the first layer pun betul. Indicate the presence of micropores ni kalau dia besar, kalau more than 200, yes. Tapi jawapan yang Mibili tu, magnitude of the absorber interaction tu betul. That is one answer, kalau dia besar, also indicate between the absorption and the first absorber layer pun betul. So boleh bagi tak 2 hadiah?
Yeah, Maybelline already won.
Maybe dah ada, maybe dah menang, maybe.
Maybe we can go to another participant.
Okay, the energy absorption in first absorber layer tu okey lah juga. Maksudnya dia sebenarnya ni tak lari pada energy. Maksudnya what I think what Sabrina is saying is that the interaction between the first and second tu that become first between the absorbent and the absorbent tu tak energy absorption in first absorbent layer. Maksud tu I think what Sabrina is saying that dia nak katakan tentang interaction antara the solid between the solid and the absorbent in the first layer. Bolehlah terima walaupun tak tepat sangat tu, bolehlah terima. Interaction. Alright. Okay.
Sabrina, right?
Bolehlah terima. Okay. Itu Sabrina kata indicate magnitude absorbent. Betul. Betul. Okay, Sabrina okay. Okay, Fiza pun betul tapi Fiza dah jawab lambat. Okay. Dia pun betul. Alright. Oh, jadi
Choose
memang
the fastest.
Okay, that means Sulaiman kata negative value is indication of poor correlation. Betul. So at least they understand what the bad concept is. Sometimes, we notice that when you get your data, students sometimes forget to refer to the C, The C value gives you a lot of, gives you quite significant information. Yeah. Whether it's small or big or negative. When it's negative, then you know for sure it's like, you cannot use the data. You have to look at other ways of improving it.
Oh. Okay, Doctor, can this
Okay.
a question, but is it want to continue with the session or question? It's
From
one
the
question there.
can we know either the compound have end-to-end pores or okay, yes. From the shape of the M Faiz, from the shape of his surface loop, you can actually know the pore shape. But then dia ada IUPAC classification and also the Deboer classification of his surface loop. Dia ada H1, H2, H3 and so on. Yeah? So you can actually look at that classification. Dia ada IUPAC classification and the Deboer classification. Look at that classification and then match your hysteresis loop punya shape with that to see whether your pore is slit shape, cylindrical or open ink bottle shape pores. Dia ada 4, I think about 4. Things like that. Okay, you can look at the shape of it. Yeah.
Let's continue with another.
Okay, just a bit more. This is actually just an extra which I thought I would like to share on the absorptive here because I found his slides and I said, oh, okay, this is something which I think we can just share, even though I've never used other absorptive besides nitrogen. I use nitrogen, but it's good sharing. I think from this which I got from the website here. So let me just go to slideshow just to see what they have here. So this is on the choice of absorptive here. For surface area analysis, we use inert absorptive gas, nitrogen, argon, krypton, some inert gas. But sometimes if you have, if you want to have reactive, reactive absorptive, these are more for chemical reaction. Yeah? I've used hydrogen when I was looking at the hydrogen absorption on carbon nanotubes. That was a very long time ago. But other than that, I've not used other absorptive. Some people use carbon monoxide, carbon dioxide. They need, even carbon dioxide can also be used for surface area measurement. Okay. So in this particular case, here, choice absorptive, here you have argon, between argon, nitrogen, carbon monoxide, carbon dioxide, krypton, methane. Yeah? So if argon is more preferable, if we don't have argon, then use nitrogen. But we know that argon is very expensive. So that's why most of the time, most of the net have nitrogen rather than argon. And argon can reach smaller pores, and it is also possible, argon and krypton also, they are possible for micropores. So you have micropores, it's better also to use argon or krypton. Okay. Okay. Carbon dioxide, in case of activated carbon dioxide, is often preferred to be the most preferred adsorbate. This takes less time and also limited to micropore analysis. So carbon dioxide is also an option if you don't have the argon or the krypton. Okay. Oops. Hold on. Saya. Oh, I think I have deleted. Oh, sorry. Oh, sorry. Those are the two. I thought I have more. Hold on. Oh yeah, I skipped the no wonder. Sorry. This should be the first slide just now. Okay. So these are the common adsorbates that we use here in physics option analysis: nitrogen, argon, carbon dioxide, krypton, oxygen, and also butane. Yeah? So if you look at the cross-sectional area, just now when I look at the formula for specific space area, I use this cross-sectional area 0.162 because I'm using nitrogen. So you can use the same formula, but just replace the cross-sectional area by the cross-sectional area of the adsorbate gas that you are looking at. Then you can use that. Otherwise, if you are still using nitrogen, you can still fix with that 4.35 times Vm. Okay. And of course, these are okay. Most of the time, because I missed this slide just now, nitrogen is the most common adsorbate used. They are not completely inert, right? And the dipole movement and thus can have localized absorption. Because when we talk about physics absorption, our assumption is that the absorption is localized. So the nitrogen, one of the reasons why we choose nitrogen is that they can have a localized absorption. Okay, and even though they may not be completely inert, but this is the best choice, cheapest choice, and the fact that they can also have this localized absorption. And just now, argon, as we said, like if you don't have, if you can have money for micropores, for example, you can take argon or krypton or carbon dioxide. Other than that, you might want to have to do a t-plot or play around with your sample size, so on. Okay, that's about it. Yeah, I think that's all. Thank you very much. In the name of God mankind, I do hope that the sharing has benefited the audience as well as me. I've benefited from the questions. I need to look at the t-plot statistical thickness. Just now somebody asked, I'm really familiar with Harkins Jura. I also need to look at that again. Thank you for the question. At least I will look at the statistical thickness next time. Okay, thank you very much.
Okay, Doctor, thank you. But do you have any quiz, another 3 more questions, Doctor?
Dia ada 3 soalan tu kan? Oh, nak lagi
We have 5. 6.
Okay, alright. Okay, so we have 2 questions. Okay,
Yeah,
next
another
question.
4 lah, another 4. If you have lah, Doctor.
Oh yeah, I have questions a lot. Okay, now I like history. I like history. What year was the paper published by Brunner, Emmett, and Taylor with regard to absorption of gases in multi-molecular layers? What year was the paper published on the absorption of gases in multi-molecular layers by Brunner, Emmett, and Taylor? What year was it?
Okay, Sulaiman already answered.
Oh,
is it correct, Doctor?
Is it 1938? Right, Sulaiman, 1938, exactly. So Sulaiman, okay.
We just move on to another question, Doctor.
Okay, berapa question lagi, Ain? Okay.
Another 3.
Another 3, okay. Another 3 question, okay. Let me just look at okay, something, maybe something simple here. Okay, hold on. Maybe some basic lah, basic. Okay, basic question. Yeah. Now, can you give me one of the assumptions of the Langmuir Isolator model? Langmuir has got three assumptions. Yeah. Give me one of the assumption of the Langmuir Isolator model.
Ng Chu Shing.
The absorption, okay, Enchusi kata mulai absorption. Yep, that means you're saying that you're saying that the Langmuir assumes only a monolayer absorption. It doesn't incorporate multi-layer absorption. Okay, so semua jawab betul ni. Sulaiman pun betul. Okay, Muhammad pun betul. Jadi orang yang pertama lah ya, Chusheng. Okay. Okay, next one. Ain ada? Lagi berapa soalan?
Another two.
Okay, two question. Alright. Okay. Okay, this one, in both model, the Langmuir Isolator model as well as the BET model, do they consider lateral interaction of the absorbed molecules? In both model, the Langmuir and the BET model, do they consider the lateral interaction of absorbed molecules? Dah ada jawapan kan? Oh, Sulaiman kata okey, Hairul Anwar salah juga. Wait. Siti Mazin kata no interaction. Okay, Siti Mazin is right. Hairul Anwar, back model pun tak consider lateral interaction. So in both model, they do not consider the lateral interaction between the molecules. So Siti Mazarina, okay. Right.
Siti Mazarina to win. And then the last one, doctor, the sixth one.
Last question, the sixth question. Okay. All right. What absorptive gas would you choose for a microporous substance? What absorptive gas would you choose for a microporous?
Shooting.
Shooting, jawab apa?
Shooting answer nitrogen, is it?
Salah, shooting salah. Fiza betul. Argon betul. You can have argon, krypton, carbon dioxide.
Sulaiman answer first, the argon.
Okay, Sulaiman betul.
Oh,
Tapi tadi
he
Sulaiman
only
dah menang
won.
kan?
Yes.
Sulaiman
Sulaiman
dah
only won the first one, so we give to Filza, can?
dah. Okay, so you can have krypton, can have argon, can have also have carbon dioxide. For apa tu?
Thank you, Sulaiman, for trying.
Okay, thank you. Thank you for trying.
Okay. I think, doctor, that's all from you.
Today, all right, yeah, that's all for me. First and foremost, thank you for your presence. I would like to apologize for any shortcomings in my presentation. Yeah, and I will remember that T plot. Yeah, siapa tadi tu, I will look at it because I always work on Hakis Jura. Is that so? If any question, you can always contact me. No problem. I will just try to help, inshallah. Thank you very much for your time. Yeah, petang-petang ni. Yeah, thank you very much.
Okay. Thank you, Dr. Professor Chemist, Dr. Zaiton, for the presentation and knowledge share to us. Okay, so beforehand, we like to all the audience to open up your camera and we will begin our photo session right after this. Please, all the audience, open up your camera. Okay.
Okay, get ready. 1, 2,
One.
3.
No.
Okay, next page. 1, 2, 3. Smile. 1, 2, 3. Okay, done.
Okay,
Okay.
thank
Thank you
you.
very much semua. Thank you very much UIRL, Ain,
Okay,
Zubaida,
Doktor.
Yana. Terima kasih semua ya. Terima kasih semua.
Okay.
Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera and a very good morning, a very good evening, morning pula.
Okay, Doktor, wait. I have the closing. Closing. Okay, there's 6 winners. Ambili 2, Sabrina, Sulaiman, Eng Choi Shing, Siti, Mazarina and Filza. Okay, our admin will privately message to the winners. Okay, and please provide your details as required by the admin. So that's the end of webinar today. We hope that we have gained a lot of knowledge so that you can implement this knowledge in your research and study. Visit the UTM URL University Laboratory Management Center Facebook and our official website for more information about our instrument services. Okay, Doctor, see you again on the third slot of Bicara Pakar UIRL 2020 webinar, first series entitled Step-by-Step Guide to 1D NMR Interpretation of Organic Compound by Dr. Siti Arianti Hashim on this 27 February 2022. Thank you and stay safe. Assalamualaikum.
Assalamualaikum. Okay, bye.
Thank you all. Thank you, Doctor.
Thank you, Ain.
Yeah.
Terima kasih. Assalamualaikum.
Waalaikumsalam.